So, we are discussing about the solution of recurrence relation, what are the different techniques to solve recurrence relations. In the last two lectures, we have discussed how to solve the linear homogeneous recurrence relation with constant coefficients when roots are equal or roots may not be equal, and with the second order equation or second order recurrence relation, we have read that how with examples that how we can solve that thing. Now, today we will see how we can solve linear, but non-homogeneous recurrence relation with constant coefficients. So, we will be reading the solving linear non-homogeneous recurrence relation with constant coefficients. So, first we see that what are the forms of non-homogeneous recurrence relation. If I remember that my linear homogeneous recurrence relation was n is C1 n minus 1 plus C2 n minus 2, C3 n minus 3 if it is of order k, then C k n minus k. This is my linear homogeneous recurrence relation. Now, if I add a function of n here, then this becomes a non-homogeneous recurrence relation, linear, since the power is of each term is 1. Okay. But then what is the solving techniques of this linear non-homogeneous recurrence relation. Now, see up to this part it is same. This is my linear homogeneous part. This linear homogeneous recurrence relation with constant coefficient. Only here this is the non-homogeneous part, that is a function of n has come. Now, this function of n, this can be of the form different form, function of n can be 2n, function of n can be of say 3 to the power n, or function of n can be n square plus n plus 1, or it can be any other that which contains some n, say 2 to the power n plus 1. So, this type of this function can be there. So, how we can solve this thing? Now, see see here that linear non-homogeneous recurrence relations, then I have two parts. If I consider that n, I have a linear homogeneous part, I have a linear homogeneous part from the above equation we see, and we have a function of n part, function of n part. Okay. Now, so every solution is of the form. Okay. Or I can write first, every solution has two parts. One is the solution of a particular solution, that means two parts. One is the solution of non-homogeneous part, we call this is the particular solution. We call this as a and second is that solution of the associated linear homogeneous part. Linear homogeneous part. Normally, we call this as the homogeneous solution. We call it is as the homogeneous solution. So, as if the recurrence relation or the equation has two parts, one is the linear homogeneous recurrence relation with constant coefficient plus this f n, that is as if this is a particular function, it has two parts. And when we will get the solution, solution has also two parts, that solution of non-homogeneous part, that means for f n, this is called normally the particular solution, and the solution of the associated linear homogeneous part we call the homogeneous solution. So, we can write that we have the recurrence relation. So, every solution is of the form that n equal to n particular n p plus n h. There are two forms. So, where n h is the solution of associated linear homogeneous recurrence relation. And in P is the particular solution. So, actually ANP I can write ANP equal to the C1 n minus 1 p plus C2 a n minus 2 p C k a n minus k p plus f n. So, I can write that if my solution B n, I can write n p plus n h. Okay. So, now with some examples we see that or how we can find out the particular solution and the homogeneous solution of a non-homogeneous recurrence relation, linear non-homogeneous recurrence relation. So, I take one example. First we take a simple example. We take an example that solve n equal to 3 a n minus 1 plus 2 n, and the initial condition is a 1 equal to 3. So, the homogeneous linear homogeneous part is, I can write that a n equal to, I can write the linear homogeneous part as a n equal to 3 n minus 1, and the f n, the function of n is as if 2 n. Okay. Now, already we have seen that the solution of this a n equal to 3 a to the power n minus 1. If I remember that our number of subsets of a set, if we remember quickly that S n equal to 2 S n minus 1, when we have framed the recurrence relation of a number of subsets of a set having n elements, we got that this is my recurrence relation, and the solution by applying the technique of iteration, we got the solution is S n equal to 2 to the power n, that we can remember. So, it is of the same form Sn equal to 2 Sn minus 1, here An equal to 3 a to the power n minus 1. So, the solution I can write, the solution it is of the solution is of the form n equal to alpha 3 to the power n. Since here there is only one linear part was there, only linear homogeneous part, but this is a hybrid type. Here it is an linear homogeneous part as well as one function of n is there. So, I take one coefficient alpha, but the solution is of the form 3 to the power n that I can get from my that simple recurrence relation that already we have read. We have solved also by iteration. So, this is of the form this. Now, I have Fn equal to 2n. So, that I can write the particular equation. So, this is linear homogeneous part and the particular solution, for the particular solution I can write the Pn equal to Cn plus d. It is of the form because it is 2n simply. So, I can write that Cn plus d, I can write 3 because my equation is 3 n minus 1 plus 2n. So, it is 3 C n minus 1 plus d plus 2n. If we remember that the way we have done a n minus 1 p, a n minus 2 p, but here I have only one first order equation. So, I have only one term. So, I have given this term C n minus 1 plus d plus 2n, because I have considered it is the solution is of form C n plus d, since my function f n is 2n. So, if I write then C n plus d equal to 3 C n minus 3 c plus 3 d plus 2n. So, if I write 2 C n plus 2n equal to 3 c minus 2 d. So, I can write this equation as n into 2 c plus 2, if I take here, plus 2 d minus 3 c equal to 0. Since C n plus d is a solution, so what I get here, since C n plus d is a solution. So, as if this is C and this is my d. So, I can write that since C n plus d is a solution, so this it will be a solution, then 2 c plus 2 equal to 0, because this is equal to 0. So, 2 c plus 2 equal to 0, that means c equal to minus 1 c equal to minus 1 and 2d minus 3c equal to 0. So, d equal to 3c by 2 equal to minus 3 by 2. So, I get the coefficients, I get the two coefficients c and d, c equal to minus 1 and d equal to minus 3 by 2. So, what is my particular solution? So, my particular solution that n p equal to is C n plus d, C n plus d, so equal to minus n minus 3 by 2. So, now we have to find out that my solution, total solution, that n I can get n is minus n minus 3 by 2 plus alpha 3 to the power n, because alpha 3 to the power n was my solution for homogeneous linear homogeneous part. So, now we can put in this equation, we can put the initial condition A1 equal to 3, that was the condition. So, I get, if that means n equal to 1. So, for n equal to 1, I have 3 equal to minus 1 minus 3 by 2 plus alpha 3 to the power 1. So, 3 alpha equal to 4 plus 3 by 2 is 11 by 2. Minus 1 minus 3 by 2 . So, I have alpha equal to 11 by 6. If I put A1 equal to 3, this is 3, this is minus 1 minus 3 by 2 plus alpha to the power 3 to the power 1. So, alpha 3 to the power 1 is 4 plus 3 by 2, I think it is 11 by 6. So, now I can write my solution, the final solution is minus n minus 3 by 2 plus 11 by 6 3 to the power n. So, this is the solution, this is the solution of that given linear non-homogeneous recurrence relation. we see another example where the function of n is of different type, and we see that how we can solve that thing. So, we take another example and I write that find all solutions of the recurrence relation five n minus 6 n minus 2 plus 7 to the power n. Five n minus 1 n equal to okay. So, we see the solution the way we have done. First we see the linear homogeneous part. For the linear homogeneous part, so we know that if we put the form of V n equal to t to the power n, that type of solution, then we get, since it is a second order linear homogeneous that homogeneous part, that means this is a n equal to 5 a n minus 1 minus 6 n minus 2. So, I get t square minus 5 t plus 6 equal to 0, and this becomes t minus 2 t minus 3, this is equal to 0. So, t equal to 2, t equal to 3. So, my solution becomes that n equal to alpha 1 2 to the power n plus alpha 2 3 to the power n. What earlier we have done that b s n plus d t n. Here s n equal to 2 to the power n. If we remember that earlier we have done that s n equal to 2 to the power n and t n equal to 3 to the power n. I have given earlier that solution is that b s n t d n, that alpha 1 2 to the power n plus alpha 2 3 to the power n. So, this is my linear homogeneous part. Now, we see the particular solution. Okay. We see here that our for the particular solution. So, my function is f n equal to 7 to the power n. So, I get my particular form n p equal to c into 7 to the power n, some constant. This is of the solution is of this form. So, if I write that c 7 to the power n n p equal to that 5 n minus 1. So, there I get c 7 to the power n minus 1 minus 6 c 7 to the power n minus 2 plus my f n 7 to the power n. So, if I divide both side by 7 to the power n minus 2, I get c 7 square is 35 c minus 6c plus 7 square. So, this becomes 49c minus 35c plus 6c equal to 49, that gives c equal to 49 divided by, this is becomes 20c equal to 49. So, c equal to 49 by 20. So, this is my particular solution. So, my final solution becomes, so my final solution it has two part, that n equal to NH plus NP, and that becomes that alpha 1 3 to the power n plus alpha 2 or alpha 1 2 to the power n. So, I give alpha 1 2 to the power n, alpha 2 3 to the power n plus particular solution is 49 by 20. So, C is 49 by 20, 7 to the power n. So, this becomes 49 by 20 into 7 to the power n. Now, if I get some conditions, like then I can find out alpha 1 alpha 2, I can find out alpha 1 and alpha 2 from the given initial conditions. Since it is a second order linear homogeneous equation, so I need at least two conditions to find out alpha 1 and alpha 2. So, there must be two conditions to find out alpha 1 and alpha 2. And solving those equations, I can get the, so once we get the, once we get the values of alpha 1 and alpha 2, we get all the solutions of the given recurrence relation. So, we have learned that how to solve the linear non-homogeneous recurrence relation. mainly non-homogeneous recurrence relation has two part, the homogeneous part will be solving the similar way we have handled the linear homogeneous recurrence relation, and only for the function of n part we will get the particular solution and the technique we have just now illustrated. So, with this we finish the lecture of the solving recurrence relation.